Hi, welcome to the video on logic behind decision tree. By the end of this video, the learner will be able to explain types of decision tree, explain Gini criterion of splitting a decision mode. Now that you have a fair idea how the decision tree works and the key terms associated with it, we will now learn about the two primary criteria which are followed to perform the splitting of decision nodes. But before that, we need to discuss about the types of decision trees. They are divided into two categories: classification decision tree and regression decision tree. We have already mentioned in the previous topic that decision trees can handle both the regression and the classification tasks. Let's first talk about the classification tree. Obviously, the target variable in case of the classification tree is categorical in nature, like the student cricket example which we discussed in the previous topic. In regression decision tree, the target variable is continuous in nature, like it was in our house price prediction example. Yes, decision trees can also be used when the target variable is continuous, and we will see that shortly. Now that we understood the types of decision trees, let's move on to understand how do we determine the criteria to be used to split a decision node. For the decision tree classifier, there are two ways through which we can do that: Gini impurity and information gain using entropy. Let's understand them one by one. Let's start with Gini impurity. It measures the impurity of the nodes and is calculated as 1 minus Gini. Let's first understand what Gini is, and then we will learn about how to calculate the Gini impurity for splits and decide the right split. Let's say we have a node as shown here on the screen. So what Gini denotes is that we pick 2 points from a population at random. What would be the probability that they belong to the same class? Let's say we have a completely pure node as you can see on the screen. Can you guess what would be the probability that 2 randomly picked points will belong to the same class? Since all the points here belong to the same class, hence no matter which of these 2 points we pick, they will always belong to the same class. Thus, the probability will always be 1 if the node is pure, and that is what we want to achieve using Gini. Gini ranges from 0 to 1 as it is a probability, and higher this value, more will be the purity of nodes, and lesser value will lead to less pure nodes. Let's look at the properties of Gini impurity before we actually calculate the Gini impurity to decide the best split. It helps us to decide the best split based on the Gini impurity. As we discussed before, Gini impurity is 1 minus Gini. So here, Gini denotes the impurity, and hence Gini impurity tells us about the impurity of nodes. Let's move on to the second property. Lower the Gini impurity, higher will be the purity of nodes, and hence higher will be the homogeneity of the nodes. Another property of Gini is that it works only in those scenarios where we have categorical targets. It does not work with continuous targets. Like if you want to predict the house price or the number of bikes rented, then Gini is not the right algorithm. Another important property of Gini is that it only performs binary splits, either yes or no, success or failure, and so on. So it will only split a node into 2 subnodes. So these were the properties of Gini impurity. Let's now look at the steps to calculate Gini impurity of a split. First of all, we need to calculate the Gini impurity for subnodes. As we have discussed earlier, Gini impurity is calculated as 1 minus Gini. Here, Gini is the sum of squares of success probabilities of each class or category and is given as P1 square plus P2 square and so on till Pn square, considering there are n classes. Further, P1 represents the probability of any 2 random data points in the node belonging to class 1. P2 represents the probability of 2 random data points belonging to class 2, and so on. Once we have calculated the Gini impurity for subnodes, we will calculate the Gini impurity of the split using the weighted impurity of both subnodes of that split. Here, weight of a node is the number of samples in that node divided by the total number of samples in its parent node. Let's look at these calculations using our model that predicts whether a student will play cricket or not. To refresh our memory, we had a total of 20 students, out of which 10 played cricket, and we splitted this data based on height of the students, their performance in the class, and the grade they belong to. Consider these two splits to understand how Gini impurity works. First, let's calculate the Gini impurity for split on performance in class. For this split, we have two categories. One is above average and another is below average. If you look at the above average, it has 14 students, out of which 8 play cricket and 6 do not play cricket. The probability of playing cricket would be 8 divided by 14, which is around 0.57. Similarly, for not playing cricket, the probability will be 6 divided by 14, which will be around 0.43. Here, for simplicity, note that we are going to round off calculations rather than taking the exact number. Similarly, for below average, the probability of playing is 0.33 and the probability of not playing is 0.67. Let's now calculate the Gini impurity for the sub-node above average. It will be 1 minus square of probability of success for each category, which is 0.57 for playing cricket and 0.43 for not playing cricket. So after calculation, the Gini impurity will come around 0.49 for this above average node. Similarly, we will calculate the Gini impurity for below average node. It will come around to be 0.44. Now to calculate the Gini impurity of the split, we will take the weighted sum of Gini impurities of both nodes, that is above average and below average in this case. As discussed earlier, weight of a node is the number of samples in that node divided by the total number of samples in its parent node. So, for node above average, the weight will be 14 by 20, as there are 14 students who performed above average out of total 20 students, and the weight for below average is 6 divided by 20. So the weighted Gini impurity will be the weight of that node multiplied by the Gini impurity of that node. The weighted Gini impurity for performance in class split will be 0.475. Similarly, we will calculate the weighted Gini impurity for the split on grade. Here, we have calculated the Gini impurity for the split on class, which is around 0.32. I recommend you to do these calculations on your own and then come back and match your values with the ones that are shown here. Now, if we compare the two Gini impurities for each split, you will see that the Gini impurity for the split on grade is less, and hence grade will be the first split of the decision tree. Similarly, for each split, we will calculate the Gini impurity, and the split producing minimum Gini impurity will be selected as the first split. Now, as you know, the minimum value of Gini impurity means that the node will be more pure or more homogeneous. Therefore, we choose class as the first independent variable for splitting. So that's it in this video. In the next video, we will look at another criteria for selecting the best input variable for splitting in a decision tree classifier known as information gain.